So what we're going to do today is we're going to talk about photon emission spectroscopy. It's actually a measurement quantitative tool where we can actually see the electron configurations. We can actually measure the intensity of electrons and get their difference in binding energy, meaning the energy it takes to remove them. And from looking at this data, we can actually verify these electron configurations, which we've been building from the solutions to the Schrodinger equation. So it's pretty cool that there is a tool out there that's verifying what we've been learning. Because it may seem like, wow, okay, yeah, n is all possible integers, and the L is what, 0 to n minus 1, and it's all wonderful, and this is what it says. But this beautiful equation and the solutions to the Schrodinger equation, the quantum numbers we've been learning, okay, have built these pretty beautiful electron configurations, meaning electrons existing as wave functions, okay, in certain energy levels based upon shape and screening and n, okay, and z. So we can actually measure and verify what we've been learning with this tool. But before we do so and get into how it works, we have to review the photoelectric effect. As you can see in the background here, I've got the great PHET demonstrator for the photoelectric effect, and it's here because the photon emission spectroscopy, PES for short, okay, is nothing more than an application of the photon, of the photoelectric effect that Albert Einstein so eloquently described in his 1905 paper. Now, let's review these things, or these components of the photoelectric effect, because it's same components that we're using for photon emission spectroscopy. So if you remember, if the intensity of the light drops, or if we start this way with the intensity of the photons, I have it set for the bundles of light called photons. If I increase the intensity of the light, okay, notice no matter what, how bright I make this, these photons hitting this metal, I have the sodium set up, does not eject any electrons. So no matter what the brightness is, it's only when I change the frequency. Now, of course, this is the wavelength here, but as I make the wavelength smaller, I'm increasing the what? I'm increasing the frequency, the color of the light, but the energy per photon. And it's only when each photon carried by this light source has enough energy to overcome the threshold, which is the binding energy that holds them, can we do what? Emit the light. So once I pass the threshold uh, for each individual element. And that, of course, threshold's different because elements hold on to electrons in different energies. Hello, they're quantized. Okay, we can see that electrons are emitted. Okay, now it has here show only the highest electrons. I'm going to uncheck that because there's going to be different speeds. Now let's talk about this again before we get to PES. Let's review. Of course, below, anytime that I go below this threshold, no matter what the intensity is, no longer do I have any electrons being emitted. So it's important you understand. I have to exceed the threshold, okay, which means each individual photon, and that's of course Planck's constant times the frequency, has to be high enough to eject the electrons. That's the most important two parts, or of the first two parts of the photoelectric effect. Now, of course, now once you exceed the threshold, okay, if I lower the intensity, there should be less electrons being emitted. Okay, why? Because there's less photons. Remember my analogy, if each photon has a person with enough money to buy, let's say, a shrunken head, only when you have what? More of them can you eject more electrons. Now, in theory, I guess we should have more electrons happening for each particle being hit, but you get the idea. So as I increase intensity, there are more individual photons with enough energy to remove the electron. And of course, as intensity goes up, okay, there's going to be an increasing number of electrons emitted. Okay, and of course, the fourth and most important part where we're going to use is that once we exceed the threshold, if each photon with a certain energy, okay, has even more energy, you're going to notice that they travel faster. So if I increase, forget about the intensity, but if I increase the energy per photon by increasing the frequency, by lowering the wavelength here, you can see that there's going to be what? Electrons moving faster. And so one of the most important parts of the photoelectric effect is that the kinetic energy that these electrons have, okay, is directly proportional to the energy in the photon. So what Einstein said is that each photon, each particle of light, okay, remember it's the particle mass particle duality that Einstein first talked about. He said that the energy of the photon, if it exceeds the threshold energy, it's going to eject electrons. But we all know that electrons from our work this week are not held with the same energy. Some electrons, like our core electrons, are closer, and some electrons are farther apart, the valence. So some electrons, okay, are held with different binding energies. Now, if I exceed the threshold and I'm ejecting electrons, the kinetic energy is the extra energy beyond the binding energy. So if you remember, okay, I'm going to write this the best that I can. All right. So if you remember, we know that there's the energy of the photon. Okay. And I'll put this as E of P. And it goes, let's say, right here. And I'll draw this arrow all the way up. Maybe. Okay. And we're just going to make a little arrow. So that's the energy per each of these particles right here. Okay. Now, I have clearly exceeded the threshold frequency, or the energy per photon. I'm going to change this and make this a nice other color. So this right here, this color, this arrow represents, let's say, a binding energy, okay, of an electron that is held in a certain orbital and a certain energy, principal energy level. Okay. Now, the other part of the arrow would be the extra energy. So if I have a photon with a high enough energy, okay, the blue would represent the binding energy, and the extra energy would be the kinetic energy. So the motions that we're seeing right here is the kinetic energy. That kinetic energy is what the motion of these electrons is what we're seeing here. And so because electrons have different binding energy, and the energy of the photon has to be equal, the total energy per particle has to be broken up into the kinetic energy and the binding energy, it should be clear to you, this is the binding energy of the blue here, okay? So once we exceed that binding energy, okay, any extra energy left gives the what? The electron the energy to move, okay? And that's what we're seeing here in this demonstration. Now, it's interesting to note, and as we know, guess what? Different electrons in the atom are held closer or far apart. There are stable and unstable. So this binding energy will change. If electrons are being removed closer to the nucleus, well, you should understand that those electrons are more stable. The binding energy is higher. This arrow goes up, and I'll draw it here. The arrow will be bigger, and guess what? The kinetic energy will be smaller, and therefore electrons that are moving slower are the result of less kinetic energy available, because a lot more energy of the photon was used to eject and overcome the binding energy. Now, the opposite is also true. If the binding energy is smaller, okay, like we're moving electrons that are what? Farther from the nucleus, they feel the nucleus less, the unstable electrons, the valence electrons, then a smaller part of the photon's energy is used to remove them, and they will have a lot more extra kinetic energy, and they'll be going faster. So what the photon emission spectroscopy does is take the different speeds once we've ejected all electrons and try to come up with something called intensity. How many electrons, okay, are going at certain speeds, and try to relate that to the different binding energies. Meaning, hey, if you have a 1s2 electron, that 1s2 electron is going to have a higher binding energy and a lot less electrons than, let's say, a 2p electron, who's going to have a weaker binding energy. All right, so let's go talk about how this all works without this good simulator. All right, so let's do that. So what we have here is the energy of the photon, and of course, long as the energy of the photon exceeds the threshold frequency, we eject electrons. And any extra we have electrons moving at some speed. As I just mentioned, if these arrows, of course, are change, if we have a binding energy of electrons that are closer, then you're going to have arrows for the binding energy greater. Okay, so the reason why that works is because the energy of the photon is equal to the binding energy plus the kinetic energy, as you can see here, as long as we're over the threshold. Now, if you rearrange this and solve for the binding energy, it's equal to the photon minus the kinetic energy. So what we do in photon emission spectroscopy, or PES, we start with a photon, okay, with a certain known energy level. So we have a certain, let's say, X-ray, and we use an X-ray because of a known frequency, because we know that that X-ray will remove all the photons. It has the energy that's high enough to remove all of the electrons, and that's what we're after of the sample. And then, of course, we have to have a way to figure out the kinetic energy. And this kinetic energy is done like this. So how do we build this? Okay, so what we have is, if it's a gas particle, we could have a beam of atoms if it's shooting a gas. Okay, so we can shoot a beam here. Now we can also take this X-ray photon, all right, of HV. Okay, that's some energy of an X-ray. All right, and what we can do is we can shoot that incident beam right there. Now, what's going to happen, of course, is we're going to inject electrons. They're not blue, but I'll just do that. And we kind of focus it by making sure that it comes out of a small opening. And so we have electrons coming off this. Now, what we do is we have some hemispheres, okay, some circular objects here. And of course, there's many ways to build this, but this hemisphere, at least the top part, is normally going to be negatively charged. They call this a retarding voltage, and they know this voltage, okay? And this bottom one could be positively charged. And the idea behind this is that we're going to shoot this beam of electrons, and they're all going to have there's going to be many different kinetic energies, because all electrons are not held in an atom. Remember, this is a beam of atoms of a singular type. Okay, of course, we can do photon emission spectroscopy with, of course, compounds as well, but we'll just start with atoms that are made of the same arrangement of electrons. Now, this beam hits here. Now, the faster moving beams are going to be less affected by that positive charge. Now, the retarding voltage makes sure that we still curve it, okay? And of course, this beam, of course, it won't be that curvy, is going to hit a detector plate. And that detector plate eventually will measure a current, okay? So if electrons hit this plate here, you'll hit a current. And so a current is detected. And then, of course, we'll put a different beam, say magenta beam. So if a slower moving electron, of course, a slower moving electron, okay, means that the binding energy is greater, okay, because you're using most of the energy of the X-ray to remove the electron. There's less of it if this arrow is bigger. Okay, move slower, and it's going to be attracted more to the positive, and it's going to hit the beam in this direction. And again, we measure the amperage, or the current, that occurs at these positions. And we can basically knowing the voltage, because we actually tune this, by knowing the voltage, okay, we can actually come up with the kinetic energy, okay, to move the compounds. Kind of like you saw in the mass to charge ratio experiment from J.J. Thomson. And so getting the kinetic energy from this experiment and knowing the exact energy per photon of a particular frequency, we can actually measure not only the binding energy of different electrons at different speeds, we can actually measure the intensity. And what does that mean? That means I can measure a relative amount of electrons. If there are more electrons in the p orbital, okay, they'll have a higher intensity here than a Than a 2s orbital holds 2, and we can actually measure that relative current, which is really cool. So let's go look at some data from a spectrum of data that we get to start to see how this technique, again, nothing more than a application of the photoelectric effect, actually helps us verify that these electron configurations actually exist. Let's do that. Okay, so what we have here is intensity. And now the intensity that is on the y-axis really represents the number of relative amount of electrons. Okay, so here is an energy level. Now notice the energy level is highest over here. Okay, and notice it's lowest this way. But in this case, you only have one peak. Okay, and looking at this peak, it may be difficult to figure out compared to others, but we have a little peak here. And we have electrons being held with a certain energy level. In fact, that energy level is pretty low. So this probably is speaking to the idea that we're dealing with hydrogen or helium. Until we look at other electrons, we can't really decipher that. But this is a peak of electrons, okay? And in fact, for all intents and purposes, this is hydrogen, okay? Just to let you know, it is hydrogen. It's a hydrogen atom, okay? And it has one little peak. And we should know that this represents 1s1. Okay, and so let's do that. So let's go on to one that has multiple electrons. Now, if we look at this, again, this is peak intensity. This peak is twice as big as the peak that we had here. There's twice the number of electrons. And if we look back on, if you just can record back, you'll see that the other peak, okay, actually was over here. That other peak was closer to this side for hydrogen. So what's happening with helium? Well, helium has 2 protons. So this is the PES spectrum for helium. And because helium is 1s2, okay, I want to get rid of this color here, 1s2, there are 2 electrons compared to the 1s1 that was in hydrogen. So there's twice as many electrons. So we use the y-axis, the peak intensity, to get a essentially whole number difference of how many electrons. And notice something. Whereas hydrogen was over here, helium's lowest energy level for electrons is shifted to the left. And why? Higher energy. There are 2 protons, okay, that of course, helium have, that hydrogen doesn't. So as we add protons, what did we learn? We learned that the orbitals start contracting, which means they get closer to the nucleus, which means the energy level, remember, this is binding energy, okay, that we get from the experiment is higher. So let's go on to lithium. So we go on to lithium, okay? What's so special about lithium? Well, it's a cool atom. It's atomic number what? 3. Okay, therefore it's got 3 protons. It's an atom, so it's neutral. It's 3 electrons. And we can account for those electrons. Now we have 2 peaks here. Notice one peak is twice as big as the other. So this number of electrons, or peak intensity, is telling me that there are electrons hitting the detector that have twice the intensity, twice the number of electrical hits, twice the number of current being occurring, because there's twice the number of electrons in this orbital. And so what's the orbital that has twice the number? Well, what do we know? This is 1s2, 2s1. This is the 1s2 what? Orbital. And it has twice the number of electrons. It's twice as high, okay, as this one. So this must be the 2s1 orbital. Notice the 2s1 is more unstable. It's farther from the nucleus. It's easier to remove, so the energy, okay, the energy is lower for orbitals farther away. These hits here are telling me that I'm dealing with electrons that are what? Closest. This is, and of course, higher energy to remove. Now, when you think about the detector, when we have these hemispheres, okay, I want you to understand this, is that where would this hit? Well, the one with the higher binding energy, okay, is going to have a smaller what? Leftover energy for the kinetic energy. So that's going to move slower. So the one with the higher binding energy hits here. And it just so happens this peak would be here. And there's twice the number of hits here. So there's twice the current. The electrons that were going faster are going to overcome those positives and travel here. And they're going to hit this half as often. And that's what this peak is here. Okay, so it's pretty straightforward. So let's continue on with the next element. And this should be getting easier. Notice the lowest energy peak is going what? Going farther this way. This is beryllium. Okay. All right, beryllium's atomic number 4. Okay, so it's got 4 electrons. And as we know, it's 1s2, 2s2. Okay, well, the one with the higher binding energy is the 1s2, and this is, of course, the 2s2. And notice there's 2 electrons in each of these 2 orbitals, so the electron intensity is the same. It's just that simple, party people. So now I'm going to just kind of go on and just give you some random ones and see if you can identify which ones are which. Now understand, these PS could be tuned to only see certain numbers, okay? I'm going to show you all of them out there for simplicity. All right, so what do we have here, party people? Okay, look at the peak intensities. I know it says number of electrons. I like peak intensities. I know I'm giving you that too, but sometimes you won't see this value here. All right, so understand you won't always get 1, 2, 3, 4, 5, and 6, but it's important to realize that these intensities, okay, they won't have the numbers here. So what do I know? I know that this is what? The same peak here. I know that this peak has the greatest binding energy. It's closer to the nucleus. So there's my 1s2. Hey, the other peak that is what? Twice, or this, I'm sorry, the same peak intensity, but takes a greater amount of energy to remove must be a 2s2. Now I know it's 2s2 because these peak intensities are the same. Now notice this one right here, this peak right here is what? 3 times as big. And it's, notice it's pushed over just a little bit. This is my 2p what? 6. Notice that the P is close in energy to the 2s because these guys are sharing a very similar proximity. The P is kicked out a little bit because the S shields for it a little bit because of the shape of the dumbbell of the P. Imagine that. This is verifying our electron configurations. And then we have a peak pretty far away, and it's half this peak. Well, guess what? That must be our 3s1. Notice between energy levels, there's bigger distance in energy, right? This is the S level closest in that shell. This is a second. There's going to be bigger leaps in between energy levels. We're verifying. Okay, let's go on to another one. I'm going to take away some data, see if you can figure it out. But before I do so, who is this? That's 1s2, 2s2, 2p6, 3s1. Of course, this is sodium. This is the photon emission spectroscopy or spectrum of sodium. All right, so our next one here, I took away the number of electrons and took away the peak intensity. And this is basically what you'll see here. And sometimes you don't even have these lines here. So you can pause this and try to tell me what you think the photon emission, who this element is. Okay, so pause it, take a look at it, use what I've taught you, and try to figure out what this might be. Okay, once you're done pausing me, okay, let's figure this out. Well, this lowest peak must be the core electron, or at least the energy level of the what? N equals 1. Right? It's the highest energy, okay, highest energy principal energy level here. So this is going to be 1 right here, 1s2. I see a peak that's exactly the same size. Not how close these guys are. This is going to be 2s2. I know I'm a new energy level because of that big gap, all right? And that's why what? The atoms of chemicals are quantized. There isn't any electron energy. There's an electron energy here, and there's a big leap in energy here. Pretty cool. And then we have probably in the same energy level. This is definitely going to be a 2p right here. Why? Because this peak is 3 times as tall as this peak. Then there's a big gap in between, and then I have a peak intensity that matches this. Hello. So this is 2p6. I'm sorry, because it's what? 3 times the peak of this. If there's 2 electrons here, the 3 times 2 is 6 electrons. Now this peak is right here with a big gap in between, is also is an s orbital, and it's going to be 3s. Big leap away or in between is telling us that that must be a new principal energy level. And now we know there's another probably orbital of the same energy level because it's pretty close, but this one's twice as big as this one. So that means that if this is 2 electrons, 3s2, because it's the same size as this one, this must have what? 4. 3p4. And you can count the exponents if you want, but 1s2, 2s2, 2p6, 3s2, 3p4, this would be the PS diagram of sulfur. Okay? So again, very cool. All right, and there's nothing more to that, okay, other than understanding that the, again, higher energy, the higher binding energy orbitals, the orbitals or electrons in orbitals that are held more tightly are going to be more stable ones closer to the nucleus, and the lower energy orbitals are the ones that are farther away with lower binding energy, and of course these would have higher kinetic energy. Okay. Okay, before I finish up, I just want to show you, if I run these PES diagrams, now what I'm going to show you is this bunch of these PES or photon emission spectrums for the elements. I'm going in order. Okay, I want to run through them quickly. I'm not going to give away what they are because some of them are going to be in your form, but look what happens. So I have hydrogen here, and then as I add a proton, okay, what's happening to this first peak, which of course this peak and this peak, this is hydrogen. And then helium has what? Twice as many electrons. But notice the shift in the peak to the left because of what? 1 more proton. Then I go to what? Lithium. I have 2 peaks. One is twice as tall as the other. And what's happening? That peak to the left right here, okay, is our still 1s2. And watch what happens as I scroll through these quickly. What happens? We'll start with hydrogens go to helium. Let's add some more. And what's happening as I add more and more and more? They're shifting where? Where are they shifting? To the left. Take them away. It's all about the proton. This is one proton. Okay, this is 16. This is our sulfur we just did. So go back. They shift away. So that you can see the Z number, okay, is really where the energy really dominates. And the Z number, of course, is associated to the atomic number. And that's why atoms differ by the atomic number. Hope this helps.